All right, section 4 from chapter 10. Lots of questions on this one. Tons. Lots of confusion. I'm going to show you a couple. And hopefully with these, you can answer the rest of the questions. Because a lot of these problems are the same idea, just with more practice applied. So looking at this, it says we know the sum of our roots is -1. So the answers to our quadratic equation must be adding to -1. And those same answers, those roots, must multiply to -15/4. It says find such a quadratic and then find the root. So this is similar to a problem we had a couple sections ago. But this time, we've got a fraction here. So we know the sum of our roots will always be equal to the opposite of b over a for our quadratic. And again, our quadratic will always look something like this in its non-factored standard form, right? Where a, b, and c are constants coefficients. And then here, this will be c over a. So I'm going to say, why don't we just call a 4, right? That way the bottom kind of matches up there. And then c will be -15. Well, if that's true, and a is 4, what does b need to be so that when I divide it by 4, I get -1? Well, of course, since there's already a minus sign there, right? We get that minus sign for free. B needs to be 4 as well. So that when we divide this, we get -1, and then we divide this, we get -15/4. So that means, for those of you playing along at home, A must be 4, B must also be 4, and C must be -15. Now, there is another way to solve this. You could say, as we've said before, let's assume A is 1. Well, if A is 1, what divided by 1 gets you -15/4? Well, C would just be -15/4, right? Because this divided by 1 still gets you that. So you could have your C value be -15/4. And you could have your B value, again, if A is 1, you could have your B value just be 1, right? You'd get fractions for your quadratic, but whatever, who cares? For me, I just went with 4, and I solved that way. So we're going to have 4 for A. So our quadratic is 4x squared. We'll get 4x. Again, the opposite of b is what we want here, right? That's what we get. And then we'll have -15 equals 0. The other quadratic you could have had, just to be clear, could have been x squared plus, could have been, plus 1, so just plus x. And then it would have been -15/4. Hopefully you can see that if I multiply everything by 4, using our multiplicative property of equality, that would get rid of the fraction and make it look like this. So it's the exact same thing. So once we're here, now we can factor. Now the catch is that I'm going to have some options here. There's a couple ways to multiply to 4x squared. You could do 4x and x, or you could do 2x and 2x. Now we do know whatever our answers are going to have a product that's -15/4. Here, let me erase that up. -15/4. So it's probably going to be this one. Probably going to be that one. That's what I would think. Ooh, actually, no. I think it's going to be this one because they'll both be divided by 2. Yeah, and then they'll multiply to be divided by 4. So I bet it's this one. But let's play around with it for a bit. We need numbers that multiply to -15. So we're going to need a positive and a negative. We said this one's the one we think it's going to be, so I'll try that. Doesn't matter where I put the plus or minus since they're both 2's here. So I would have checked this one first anyway, just because this one's going to have more options. And 5 and 3 or 15 and 1 are kind of the numbers I need. If I do 5 positive and 3 negative, I think I win, right? Because 2x times 2x is 4x squared. 2x times -3 is -6x's. And here I get 10x's. So 10x's minus those 6x's does get us 4x. And of course, this gets us our -15. Cool. So yeah, this is another reason why it's useful to understand this idea, because it can help you figure out which one you want to go to. First, I know our answers are going to multiply with a denominator of 4. So this is probably what I want. They're both going to be over 2. This one would be over 4, that one wouldn't, but they'd still kind of multiply to that. I don't know. Having commie denomies also works nicely to have a whole number here. But anyway, here are our answers. We're going to get -5 halves, and we're going to get 3 halves. And you'll notice that these will multiply to negative 15 over 4, which is what we wanted, right? And they will add, because they have common denominators, to 2 over 2, sorry, negative 2 over 2, which of course is negative 1. So, yep, that's what we needed. All right, so let's take a look at 10.4.4. Again, this entire section and probably the next one are all kind of spicier questions, right? So here's this quadratic, which isn't even equaling 0. We need to move that over, right? And it says whatever the answers are, right? The roots, our solutions, they're going to call them R and S. So we get some answers from this. There are two numbers that we plug in. We're going to call them R and S, and they make the whole thing equal 0. They say take those answers, those roots, add 3 to them, and multiply them together and figure out what you get, which is kind of suspicious, right? So you could try and factor this whole thing, right? We could write it out, 30z squared. Then we've got negative 7z. And then if I subtract 68 from both sides, we end up here. And I need numbers that multiply to 30. There's quite a few. And I need numbers that multiply to negative 8. There's quite a few. And it's negative, so I need a plus and a minus when I factor this. Oh, this is kind of nasty, right? You can totally do that. Find your roots, figure out whatever they are, and then plug them in here and multiply, right? But I'm going to do this. I'm going to distribute. I get R times S, and I'll do that in red. You know, they want us to multiply these together and figure out what they equal, so let's just do that right away. We get R times S. When we multiply that R and distribute it to the 3, we get 3R. Here, we're going to get 3 S's. And I will do that in the same color. And then over here, I'll do in green. We get 3 times 3, which is 9. So apparently this multiplies to this, and if we knew what R and S was, I could tell you what number it equals, right? We just plug those in, we'd be good to go. However, there's something I want to point out about why this is helpful. This, since R and S are our solutions, they're our roots, right? R times S is just those roots being multiplied. That's the product of our roots. And we know the product always equals C over A. And we know what C is. C is negative 88. And we know what A is. It's 30. So we know this is negative 88 over 30. That RS part right there must be negative 88 over 30. Now, here, it's going to be hard to see this at first if you don't have really strong algebra skills. But I can turn that into the sum of our roots. And by the sum of our roots, I mean R plus S, right? That's the sum. Well, because they both share a factor of 3, I can rewrite this as 3 times the quantity of R plus S. So there's our sum of roots. So if only we knew the sum, we could replace it without even needing to know what R and S are. Just like we don't need to know what R and S are to know that they must multiply to negative 88 over 30. Well, the sum of our roots always is going to be negative B, the opposite of B, over A. Well, we know this is negative 7. So that means this, our B value, must be positive 7. Sorry, positive 7. There we go. So B is positive 7. And our A value, of course, is 30, right? Well, hold on a second. I knew I goofed this up. So it's the opposite of B. So what's the opposite of negative 7? It's just 7. There we go. So 7 over 30 is what we get when we do negative B, the opposite of this. That's what that means, right? Negate it. If you negate a negative, it comes out positive. And then A. So all in all, our equation becomes this. The RS becomes negative 88 over 30. This blue part becomes plus 3 times whatever R plus S is. And we know R plus S is the sum of our roots. That's 7 over 30. And then we still have that plus 9. So without figuring out what our roots are, without having to factor this awful quadratic, I can use my properties of the roots that they multiply to C over A, and that they add to negative B over C. And I can use that to figure out what'll happen with this, right? What'll happen when I multiply those. So now we distribute that 3, we multiply, and then we try to get commie denomies. So I'm actually going to keep that 30 since these have commie denomies right now. And I'm going to write this as negative 88 over 30. And instead of dividing out and making that a 10 and that a 1, I'm going to make this 21 over 30, which I know could be simplified. Then for this, I need 30ths for that 9. Oh boy, there we go. So I multiplied that 3 times 7 and left it as 21 over 30, so they'd all have the same denominator. And of course I need 30ths here. Well, if you think about it, if the top were this, I'd get 9, right? So the top must be 30 times 9 if it's still going to be 9. So what is 30 times 9? It's 270. That's how many 30ths are in 9. 270. If you divide this, you still get 9. So when I put these all together, looks to me like this is 291 30ths. And then I have negative 88 30ths. So basically it's 291 30ths. And I'm taking away 88 30ths. So what I'll be left with is 203 30ths. And that is the answer to this question. What happens when you multiply our roots plus 3 together? Well, apparently you get 203 over 30. Didn't need to factor this. Didn't need to find those roots. I could instead use my properties of roots to get this. Cool. All right, so that's 10-4-4. All right, so 10-4-6 is the last one we have to do with a star on it. It says if m and n are the roots to this equation, meaning that m and n are some numbers that when we plug them in here, make this whole thing equal 0. But not only that, they're also the coefficient of our linear term and our constant, so that's interesting. Of course, m and n can't be 0, because if they were, then this would be gone. Pretty boring equation. What number does m plus n equal? And hopefully, you're thinking like this. This, since m and n are the roots, this is our sum of roots. So they want to know what the sum of roots equals. Well, the sum of roots always equals negative b over a. And, of course, from our original equation right here, a is 1, b is m, and c is n. So apparently, m plus n, sum of our roots, will equal negative b over a. Well, that's just negative m over a, which is 1. Well, that means we get this. Interesting. If I rearrange this equation, it looks like I get, after adding m to both sides, 2m plus n equals 0. So in other words, n is negative, or the opposite sign of this, and it's half that, so that when you put them together, you get 0. So that's an interesting thing. But I still don't know what m plus n equals. I need to figure that out. Well, what about the product of our roots? Maybe we should think about that. Well, a product of our roots is always c over a, which in this case is just n. So we know that m times n must equal n. Well, that can only mean one thing. M equals 1. Right? Only 1 times n will get you n. If you're not sure about that, you could divide both by n, and what you would get is m equals 1. Same idea. So if m is 1, now we can actually solve this problem, right? We have 2 times 1 plus n equals 0. So we know that n must equal -2. And so if we know that n is -2 and m equals 1, we can actually answer their question. What is m plus n going to equal as a number? We knew it as an expression. It equaled this, right? Well, m plus n is going to equal 1 plus -2. It equals -1. So again, just using our properties and properties of our roots, right? Both the sum and the product, we were able to deduce what kind of equation would have its own solutions, be its own coefficients. So it looks like the product or the sum of those will be -1, m will be 1, n will be -2. Again, coming from our sum of roots and our product of roots. Cool. All right, that's the last one for this. New video coming up soon.